Hi, everyone. Thank you for joining our session with Swift Package Index and Max Stadium. Before we get started, we're going to go through a few housekeeping items. This session is being recorded and will be sent via email to everyone who has both registered and attended today. You'll see that in your inbox in the coming days. Everyone who's joined has been muted, but if you have any questions, please feel free to add them to the Q&A button at the bottom right hand of your screen. We'll go through a few of the questions as they are relevant during the presentation, but we will save time at the end of our session to answer any questions that you may have. I'm going to pass things over to our panelists and hosts so that they can introduce themselves and kick things off.
Hi, my name's Dave Verwer, and I'm one half of the Swift Package Index team.
Hello, I'm Sven Schmidt, and I am the other half of the Swift Package Index team.
And we're going to talk today about the process of switching one of the major components of our system from bare metal Mac machines across to an Orka-based system. But before we get started with that, I'll just give you a quick brief overview of what the site is and why it exists and what it does. So Swift Package Index is a website that is designed to help developers find good package dependencies for their Swift applications. So that might be iOS and macOS applications. It might be Swift on the server applications. And it's effectively it's a search engine that once you search, you get to see information on packages and libraries that you could include in your Swift application. It's an open source website and has been since the beginning. We started the project in March 2020, just as the world kind of shut down, so it was perfect timing, and it has been running for more than 4 years now. So it's a relatively large open source project written in Swift using the Vapor web framework, and it's actually the largest open source Swift on server project that's at least that I'm aware of. If that's not true, then please let me know, but I think it is. I certainly hadn't had a lot of experience running an open source project before this, and I don't think Sven had either. So this was fairly new ground for both of us. So we kind of started up the project and got things running and are making the best of how we can kind of operate it day to day. When we did start the project, this was really at the core of what we hoped to do, which is help software developers using Swift make better decisions about their package dependencies. And that really goes through the whole process of the design of the what you see on the site, the front end of the site. So, for example, as soon as you look at any package on the site, you're going to see lots of metadata that we are aggregating and collecting for you on each package. So it tells you, for example, how long the package has been in development for, but also how actively maintained it is. So you can see this package on the right-hand side here has been in development for 4 years, and the last issue was closed 2 months ago, and the last pull request was merged 2 months ago. So you can see from that you're both looking at a relatively well-established package, but also one that is still receiving attention from the package authors. You can see things like the number of GitHub stars here, the license that it's made under, and that kind of thing. There's also a button on the right-hand side called Try in a Playground. So any one of these packages that you see here, you can hit that button. A little Mac app will either download or launch if you already have it installed, and it will make you a Swift playground with an empty source file for you to play around in, but it will also import this package that you were looking at in as a dependency. So very quickly, you can take any package and you can just hit that button and start experimenting to see if it's the right package for you. And again, all of this just comes back to that goal that we have on the left-hand side here, help people make better decisions about their package dependencies. Another big part of that is the README file, of course. So we bring the README file in and we maintain all of GitHub's syntax highlighting and code features and all the kind of formatting that GitHub puts on a README file. We bring that in as best we can. We also bring in any release notes from GitHub to show if you want to look at a package, you want to look at what a package is doing. One of the ways you can do it is to look back through the history of the releases of the package. But the thing we're really going to talk about today is this area in the center here, this compatibility section. And this is where things kind of get interesting on the site. So the idea for this feature came about in kind of week 2 or 3 after we launched the site initially. And we had no way to tell developers which versions of Swift and which platforms each package was compatible with, because that information just doesn't exist in the package manifest file or in GitHub or in any of the sources. That information just doesn't exist. And we were having a conversation with one of the people who were kind of interested in what we'd launched for this project. And off the cuff, they suggested, well, why don't you just build all the packages? And if they build, then they're compatible. And if they don't, then they're not. And we all kind of laughed a little bit when that was suggested, because it's a large job to build every package. But actually, that's what we ended up doing. And we're going to talk about this. This is going to be the main bulk of today's talk. But behind that matrix of compatibility is a lot of compute power building each package to determine whether in the real world, will this work with the version of Swift that you're using on the platform that you're using. The other major feature that we have on the site is that we build and host documentation for any open source Swift package. So Apple have a documentation tool called DocC, D-O-C-C, and that will take documentation that you put in your source code, in source code comments. It will extract it along with any additional markdown files that you put in your source code, and it will compile a nicely formatted documentation site containing all of the documentation that you put in there. And this, again, it would not have been possible without that foundation of the build system, which is doing all the compatibility checking, because in order to generate documentation, you have to have a successful build first. And at that point, you can then generate documentation. And so it fit well with what we were already doing, but we also wanted to host documentation, because by default, DocC will generate documentation locally for developers and install it on their local machine. It will generate a web version of the documentation, but it doesn't host that for you. And so what we wanted to do was give package authors a really easy way, trivially easy way, in fact, to just opt in to having their documentation hosted on Swift Package Index. And once they've opted in to do it, we'll just take care of building, hosting, and versioning their documentation. So every time they do a new release of their package, we notice that new release, we build a new version of the documentation, and we host a new version of the documentation. And you can see on the right-hand side there at the top on the kind of heading bar, it says documentation for 0.4.0 there. And whenever a 0.5.0 was released, that would automatically update to 0.5.0. If there were a major version, so a 1.x or a 2.x, we would even make the old versions prominently displayed, because if you're still using an older major version of a package, you might want to look at the documentation as it was at that point. So we're doing versioned documentation hosting for free for all open source Swift packages. And this has been a great success as well, to the point that even some Apple packages use Swift Package Index documentation hosting. In fact, you'll see there on the left-hand side, the Swift DocC package, which is the DocC compiler, hosts its documentation on the Swift Package Index, which is always a little bit of a circular reference there. But you can also see, for example, Swift Testing is a brand new package from Apple, just released a few weeks ago. Their documentation, and it's their primary documentation, is hosted on the site. So I'll just give you a very quick look at the site itself. And in fact, we'll use Swift Testing as our example. So obviously, initially, it's a kind of search engine. You can see that we've got Swift Testing coming up there, or you could just type in the word testing, if I can type properly. And you can see it's coming up as the fourth result there. We also have keyword search, so you could, if package authors have assigned keywords on their packages, you can search via keyword. And you can also search for authors, so you can see all the packages authored by a specific person or organization. But we'll go back and we'll just take a quick look at Swift testing. And you can see here in the compatibility section that it must use some language features that are specific to Swift 6 because it's not compatible with 5.10 or below. It's also not compatible with any of the other Apple platforms like iOS or visionOS or watchOS because it is a testing framework. So you're going to want to run this on the machine. It can write tests of those platforms, but this is the package itself runs only on macOS or Linux. And what I could also briefly show you here is we can, either as the package author or as somebody who is browsing the package index, you can click through and see all of the build results. So you can see the reason it's showing a compatible build for macOS and Linux is because we have successes here for this version and for the main branch, and everything else was incompatible. And you can even, if you want to, dig down even further and look at the build log for what happened in those builds, including what was the command that we ran to make this, to determine this compatibility. So we have lots of features here for package authors to kind of make sure that they're getting correct compatibility, because it's quite important that this represents their package correctly. Let's go back to the slides. Okay, so how are we doing? We are now indexing more than 8,000 packages. We started with about 2,000 at the launch, and in fact, this is a graph here of package growth over time, and you can see it's got some kind of odd little bits of, ups and downs and all the rest of it going on here, because we've been quite careful to make sure that we have a good set of packages that are actually intended to be packages used by other people. So we started with a list of about 2,000 packages, but you'll see that after that 2,000, it kind of drops a little bit. So what we did was we kind of filtered out some packages that were technically valid packages, but probably were not intended for other people to use. They were test packages or demo packages. And then you can see a huge jump, and we kind of merged with another package list at one point, so that doubled it. And then we realized that package list was full of a whole load of packages that maybe shouldn't be in the index. So at the beginning, we were kind of up and down a little bit, but after all that trimming got finished, you can see that we've just been a steady increase of packages. The green line down the bottom right is the number of documented packages. So we launched a documentation hosting support in 2022, and you can see that straight away people started to opt into that, and it's just been rising ever since. And in fact, we're now hosting documentation for about 900 packages, which is about 11% of all packages in the index. But the more important stat here is, of the new packages that are getting created and added into the index, about 40% of those packages are choosing to host their documentation on the site. So that's great news. We also are used to power a packages page on the Swift.org, the official Swift website. So if you go to the Swift website and look at the packages page, you'll see a selection that rotates every month, and that data is coming from our backend as well. So that's been our progress so far. But what we're really here to talk about today is the build system. And this is the reason that we have ended up with an Orka cluster. But before we talk about the Orka cluster, let's just go into a little bit more depth about what this is showing. So it's measuring compatibility across two dimensions, both Swift version, of which we always have compatibility testing for the latest 4 versions of Swift. So as 5.8 rolls off at some point, or as 6.1 comes around, we'll roll 5.8 off, so that we always just have the most recent 4 versions, which copes with most people's real world situation. And we also have platforms there, all of the Apple platforms, and then Linux as well. And we're planning to add a couple more platforms in 2025. We're planning to add WASM support, which is WebAssembly, and also Windows support. So Swift on Windows has been making great progress, and it's about time for us to show compatibility with Swift on Windows. So that will be another two dimensions on, sorry, not dimensions, another two platforms on that bottom list. We also aggregate version numbers. So you can see here on the left-hand side of the image, there's a row for 3.18 and a row for 4.0 and the main branch. So what's happening here is this package at version 3.18 had compatibility with all the versions of Swift that we have. And in 4, they've obviously started using some Swift 6 language features, and they're about to drop support for these platforms. And this gives developers a real good sense of whether they need to start upgrading their Swift version or something like that. So this is genuinely useful information for software developers using Swift packages, or at least we believe it is. And in fact, to get those build results, like I showed you before in the demo, this is the page of every individual build. But you can see that for a package that has 3 versions, so a release version, a beta or a pre-release version, and the default branch, it can take up to 81 builds to create this matrix of compatibility. So there's a lot of work behind the scenes going into that chart. And pre-Orka, this is what our hosting environment looked like. So we're split with our hosting between Microsoft Azure and Mac Stadium. The web servers, the staging and the production environment, databases and all the rest of that, that's in Microsoft Azure. We also have a couple of build machines in Azure that focus on building the Linux builds for the compatibility matrix, and they run through Docker. And then on the Mac Stadium side, we have, or at least we had before Orka, we had 3 Mac Mini machines that were doing all of the macOS, iOS, visionOS, watchOS, all the rest of the platforms compatibility testing. And the way that we organize this is through GitLab pipelines. So we don't use GitLab to actually do any of the builds. We do all the builds ourselves, but we use GitLab to keep a queue of all the build jobs that need doing. So the web server and the database, they go and they find new versions of the packages. So they're constantly polling every package repository to see if a new package version has been released or if the main branch of the repository has moved forward. And when they find something to do, so when they find a new version, they pop a job into the pipeline that then gets processed by the build machines. So that the build machines are all running, or they were all running, GitLab Runner, which picks up active jobs from GitLab, does the build, reports back a success or failure via an API that we expose on our web server. So the two parts of the system are completely isolated with kind of GitLab in the middle. So why would we transition at all? Well, this is what we had. So we had 3 Mac Minis, and they were powering 4 versions of Swift. And the reason that's important is that with Xcode, each different version of Xcode, which represents a different version of Swift, needs to run on a different version of macOS. So actually what we had here was we had a split at this point where we were doing 5.7 to 5.10, where the version of Xcode to compile for Swift 5.7 needed and would only run on macOS Monterey. 5.8 and 5.9s were 2 different versions of Xcode, but they both needed to run on Ventura, and 5.10 needed to run on Sonoma. So 3 Mac Minis is actually the minimum number of physical machines that we could get away with to even do this job, let alone capacity. Because it's impossible to run more than one version of macOS on a bare metal Mac. It's not something you can do. So this was our setup. But then the problem with this is that actually that middle machine, which is coping with two versions of Swift, where the outside machines are just coping with one, that one fills up with, or that one runs out of capacity much more quickly than the outside two. And we did start to run out of capacity. And so we had to think about it, and we added another Mac Mini to the mix to help us with capacity. Now, one of the things we could have done here is done this. So we could have had one machine, physical machine, to run each individual version of Swift. And as the macOS versions increase, we could have reformatted and remade these machines to run the right versions of Xcode on the right operating system. But instead, we did something different, and we started to experiment with virtualization. So we kind of knew this would be a temporary situation, so much that in our password manager at the time, when we got this fourth bare metal Mac Mini, we even titled it Temporary Mac Mini, because we were very hopeful this would be a temporary situation. And what we did with that machine was we ran two virtual machines on the fourth Mac Mini, and we manually brought up and down different VM images depending on what the demand on the system was. So if we had a backlog of builds that needed Ventura, we'd spin up two Ventura VMs. But then gradually, as that backlog came back down, we might spin up just like one Sonoma and one Ventura to cope with the average load of the system and that kind of thing. As you can imagine, managing that machine was pretty painful. This is a machine, a bare metal machine that is literally running with two virtual machine windows sitting on screen, and bringing up a different virtual machine was a case of Control C to kind of quit that virtual machine and then bring up a different virtual machine. It was entirely manual, and while it did work, it actually worked surprisingly well. It worked really well, but it was not a sustainable path to future growth. And that's where Orka came in. So we had a chat with Mac Stadium, and we talked about the potential to build an ephemeral build system where we start up a virtual machine, it does one build, and then the entire virtual machine is destroyed and goes away. And that's a very different way of working. It sounded like it would solve all of our problems, but I must admit we were a little nervous to know whether it would be a lot of work to transition across to that, and would it actually work for us. So it was a kind of big decision to kind of make that step, but we decided to do it, and well, you'll see how it went. So this would be the kind of logical diagram of what we might have seen before we. This is kind of how we were thinking about it before we started the process. Each job would still come from GitLab, so we'd still use our queuing system from GitLab. But each of these machines that you see here is just processing one build on a specific Swift version on a specific version of macOS. And as soon as that build is complete, that machine goes away and another one comes back in its place to process the next build. There was one problem that we had with this, which again was part of what was making us a little bit nervous, is that we didn't know Kubernetes. So Orka, I believe, is based upon a Kubernetes system, and that is something that neither myself or Sven had used in the past. So we didn't know Kubernetes, and we were kind of a little concerned whether that might be an issue. The solution was easy. We still don't know Kubernetes. It's great. The only interface that we use to our Orka cluster is either via the Orka API, which is our primary use of it, or via the command line tool, which you can install on your machine and manage your cluster remotely using command line parameters and arguments and all the rest of it. I believe that you can access and manage and do things with the Kubernetes system behind the scenes. But I'm not even going to try and talk about that because we've never done that. We've never felt the need to do that. I believe you can do it. We haven't even touched it. Everything that we needed it to do has been possible purely using the Orka tools. So pre-Orka, what did a build look like? On those bare metal Mac machines, what would happen is they would run the GitLab runner, and they would fetch a job from GitLab tagged for that specific machine. They'd run the build command, they'd generate the documentation, and they'd report back to the API endpoint on the Swift package index. So that looks a little bit like this. On a physical Mac Mini, we have that GitLab runner that's running all the time, and we chose a concurrency of 4 build jobs to run on each Mac Mini, because each build job kind of has some uptime and downtime during the build. So at the beginning, it's that there's a checkout of a repository, which can be quite a lengthy task in terms of the amount of time it takes, but it's almost not touching the CPU at all during that. It's just doing a download. Then it does the build, which of course uses all the CPU it can get. And then it does the documentation generation, which is again very CPU bound. But then it has to upload that documentation out to S3. So again, the CPU is not being used there. So they have this kind of up and down, uneven CPU profile, and we found that 4 build jobs kind of was about the right balance of concurrency for a single machine. So this is what our environment looked like pre-Orka. We had 3 of those machines that were just running GitLab runners and 4 doing 4 build jobs, and then that 4th machine, the temporary Mac Mini, ran 2 virtual machines, which each in place ran a GitLab runner, and we made those run 2 each to give the concurrency of the physical machines back to 4. So this gave us the ability to process up to 16 concurrent builds on the old system. In preparation for Orka, we actually needed to change the way that our builds work, because the ephemeral build machines can't run the GitLab runner. The build machines by definition are ephemeral, and so there's nothing, once a build machine shuts down, there's nothing checking that queue for what to do next. So what we did was we built a small application that actually lives in our Azure hosting, that monitors that GitLab queue and completely orchestrates the Orka cluster. So it connects to our cluster via a VPN. It monitors the GitLab queue, and when it finds a job that needs a Mac-based builder, it, via the Orka API, starts up a machine, runs the build, and then kills the machine. It also does some other very useful stuff for us. Like, for example, we have in our build scripts a timeout of 10 minutes. So if a build job, we do a best effort to build all the packages, but if the package that we're trying to build is too big, or it's maybe just the build isn't finishing for some reason, we want to stop that so that it doesn't tie up our entire compute resources. Now that's handled in the build script, but we have a second level now of this, where if a VM has been running for more than 15 minutes, we just kill the VM. Like we don't really care. Anything that's gone above 10 minutes, we're done with. We're not trying to build that anymore. So we just have this foolproof way, which is really stable, of just absolutely just saying, we're done with that job. Let's just kill the VM, and the VM disappears, and anything that it had done to that machine has gone. So the anatomy of a build after Orka is this. So now the orchestrator fetches any Mac-based job from the GitLab queue. It decides which VM image to launch based on the job that it's picked up. So it spawns a specific VM during that build process, SSHs into it, runs the build commands, generates the documentation, and reports back in the same way. And once that VM has gone away, the next time that VM is launched, so next time we need a Swift 6 build, we get a completely fresh version of the Swift 6 image. So the isolation of these builds is far better than what we had with a bare metal machine, where every single build was running on the same machine. Um, Remarkably, we didn't actually have very many stability issues with that, but it was always a worry that some package would include malicious code that would somehow manage to break out of the sandbox and kill that machine. Our entire build cluster would go. With the VM-based approach to this, we just don't worry about that, and I'll talk a little bit more about that in a few minutes. But we have now on-demand isolated builds for every build that's coming out of GitLab. The other major advantage of this system is that because we're spawning VMs based on the specific job that's coming out of the queue, we have no more kind of lumpy load problem where we had one machine that was processing two versions of Swift and two machines that were processing one version of Swift. We just launch the machine that's needed, and our cluster scales not based on the type of builds that we're doing, but purely based on the number of builds that we need to do, which again is great. So if we have a huge number of Swift 6 builds coming through the system, we just launch only Swift 6 VMs and they just get processed. So this is now what we're running on, and this is the process that we're going through for each build. And this is what it looks like. So our orchestrator runs on a separate machine somewhere, and then each physical node in our Orka cluster can host up to 2 virtual machines. And this is one of the few disadvantages, actually, which is we can only run 2 virtual machines per host or per node. And that is actually a restriction placed on macOS by Apple, in that the virtualization on macOS will only permit 2 virtualized instances of macOS to be spawned on a physical Mac. So we're limited in that way, but we have then the isolation and the security and all the rest of it as the advantages. And each of those virtual machines just runs one job, because it kind of has to just run one job, because if a virtual machine were running 2 jobs, you'd need to wait for both of them to finish before you could kill the VM, which it ruins all the advantages of this system. So each VM just has to run one, but as soon as that job finishes, the VM also goes away. And so if we'd have had 4 physical machines, like we had 4 physical machines in the old version, unfortunately, our concurrency would have been halved. Now, each build is operating faster because the amount of resources being assigned to that job is significantly more than the old machines that were running 4 at the same time. But what we did realize is that as we designed the system, we would need to keep our concurrency at about 16 builds. And so we ended up doubling the number of physical machines that we had to run this workload, which is, I mean, I think the title of the webinar was building 350,000 builds a month, those are the numbers that we're doing. So we're doing quite a large number of builds per month, probably more than the most CI systems might require. But we did end up needing to double the physical hardware to keep the concurrency the same. And so this is what we're looking at now. This is what we run day to day today. We still have effectively the same setup on Azure, 2 Linux build machines, all of our web servers and production staging. And now we have, on the right-hand side, we have an Orka cluster of 8 physical machines that process all those builds. So how's it going? Well, to quote me right now, it's going great. There's not much to say really about how it's going. It has been incredibly smooth once we switched over to a production setup. There was a fair amount of work to get to that state. We had to, as I say, we had to kind of write that orchestration software, which you may or may not need to do if you're thinking about doing this. Part of the reason we needed that was because we have this logic that needs to operate during the build process. So you pull down a build, off the queue and then have to decide what kind of machine to load up. And that's partly why we needed to write some software there. There is, I believe, a GitLab runner. If you just want to do a GitLab runner that will spawn machines and do that kind of built in. But we had to go just one step further than that. So there was a little bit of work set up. And during the process of switching across to production, we ran both systems in parallel for a little while. So we still had our old system that was the kind of tried and true, we know this works, and then we'd give different workloads to the Orka cluster to test it out, see if it was going to, see if our software was working, see if the cluster could kind of do what we expected it to do. And then over time, we were comfortable with what was happening there, and we got rid of the old system and moved across to Orka in production. And it's allowed us to do some really quite interesting things this summer. So one of the things we've done is, like I say, there was a new version of Swift this summer called Swift 6, and it included some data race safety language features. And one of the things that we were curious about was whether packages in the index were taking advantage of those data race safety features, and they would show as errors in the builds. And so what we did was we ran regular rebuilds of 100,000, I think it was about 110,000 builds per run, with every single Swift beta throughout the summer. So every beta 1, beta 2, beta 3, what we would do is we'd kick off 110,000 builds to compatibility test with that beta, that specific beta. And we plotted the number of compatible packages increasing over the summer. And you can see it's a fairly shallow slope on that line, but it is a slope increasing. More and more packages were taking advantage of those compiler features, and we were able to visualize that data, which that data just would not have been possible to get without a build system like this to be able to very quickly and efficiently process hundreds of thousands of builds. It was also a great stress test for the Orca system because each of those 110,000 build runs took about, it would saturate the cluster for about 6 or 7 days. So that is having the cluster under load, under maximum load for multiple days, which is a great indicator of stability. And we didn't see any stability problems at all, which was fantastic. We've also built a couple of internal tools that we use to monitor the cluster. So as I say, we have the orchestrator that we built, which there's no screenshot of that because it's a very dull, it would be a very dull screenshot. It would be a black terminal window. But we did build a couple of tools to keep an eye on our cluster. So we have this one, which is refreshes every few seconds, uses the API to see what's currently running on the cluster. So we can see each individual build, and you can see on the right hand side here, they're all built 2 minutes ago, 1 minute ago, 58 seconds ago. There's a couple in there that have been running for 8 minutes, so if they don't finish up in the next 2 minutes, they're going to get killed, but that's okay. And right clicking on any of those, we could even VNC in to interact with that build if we were looking at specifics of that. We don't have to do that very often, but we have that ability if we need it. In terms of disadvantages, there's a couple that we found, but they're fairly minor. One is that virtualization on macOS, and this is not specific to Orca, this is just virtualization on macOS, very rarely is able to update the operating system version. You get this fail to personalize software update error, and it just won't update. But when we were running bare metal Macs, keeping the operating system up to date was quite important because you're running lots of builds through that, and so you want to be running the latest version of macOS for security reasons and all the rest of it. If you're running an ephemeral machine, even if it were not behind a VPN, which it is, that machine only exists for a few minutes. And so the impact of being not on the latest version of macOS is almost not not important at all. We've actually stopped worrying about it because first of all, they're all hidden behind a VPN, no external access to them whatsoever. And each of them only runs and then rolls back any changes that are made when the build finishes. So this is a disadvantage, but it's not one that really troubles us very much. And the only other one is, as I mentioned, the fact that a physical Mac can only run 2 virtual machines. If Apple would allow 4 virtual machines per physical Mac, we could make much better use of the hardware that we have. We could keep that hardware much more utilized based on that restriction. So that would be a real huge advantage if Apple ever did that. But I don't see any signs that they are looking to do that. But that would be great if they did. And the main point to make here is that this cluster has given us an easy path to future growth. We previously were managing all of our bare metal Macs manually. So if we needed to move the operating system version, we would format the machine, have to set everything up from scratch, have that. It was also very difficult to make sure that the Macs that were running the same operating system version were actually set up in the same way. And we had scripts and we had kind of sets of instructions to make sure that if a machine was set up, that it would be set up in the same way. But you never execute those scripts exactly the same way. You never run those instructions perfectly, and so we did okay with it. But there were differences on each of them. With the VMs, we know that each VM is set up in the right way because it spawns the same VM over and over again. And so where scaling our previous solution was fraught with, well, that's going to be a lot of work. Scaling from where we are now is purely a matter of adding more physical machines into that cluster. Um, and that's really all I have to say today. So thank you so much for listening. Both Sven and I are available for any questions that you have now. Please go check out the site if you haven't already. And I believe Andrew is also available for questions on the Mac Stadium side if anyone has any of those. But thank you very much for listening, and that's all from me.
Thank you, Dave. Very, very well presented. I'll actually ask the first question. Um, the value you see in partnering with Mac Stadium and using Orka specifically, and for folks on the call, I'm Andrew Bojack. I'm the product manager for Orka, so obviously a vested interest. But when you opened, you talked about some of that manual pain of mixing Swift versions to the underlying host Mac OS version. You largely benefit from the fact that now it's vanilla. You don't care anymore. I'm assuming
Yep.
that all of your hosts are on the same OS, and you just worry about trying to get it working in the ephemeral VMs at this point. Is that where you're at?
Yeah, so in fact, all the hosts on Orca, we actually don't know what version of macOS they're running because all we interact with is the API saying, please make us a machine, destroy a machine, whatever. But we have a set of virtual machine images set up for each macOS version that we need. So we have a Swift 6 image, which will spawn a macOS Sonoma virtual machine. We have a Swift 5.9, which I think also spawns a Sonoma, but has a different version of Xcode on it. And then we have some Ventura images as well. And each of those VM images defines which version of the operating system we boot up. So we do have to still create the VM images. And when there is a new version of Swift, we do create a new VM image. But that compared to, we only do that once, no matter how many machines are in the cluster. And that process, and again, we're getting into the weeds a little bit here, but our previous system ran every build in a non-admin user because we were concerned that Swift builds, even if they were able to break out of the sandbox, what would they get access to? So we gave them a less privileged account. On the VM images, we just run everything through as admin because those VM images are ephemeral. If a build manages to do something to those VMs, the worst it can possibly do lasts for about a minute.
Ladies, it looks like there's a couple of Q&A questions.
Sure thing. Happy to help. I don't think I can see those questions, so if somebody could.
Yeah, I've just answered a couple. Just looking at what the next one is. How much longer does it take for a start? Yeah, so the question is, how much longer does it take for a job to start as it has to spin up a VM first in comparison to a bare metal runner? You
It's a
wouldn't
great question.
notice.
Yeah.
It takes less than 3 seconds for the VM to come live, and the GitLab runner, even if it pulls directly, has a delay as well, and you would not be able to tell the difference.
That was actually one of the things we were a little nervous about before we did this, and I was stunned at the speed of starting up a VM. It takes well less than 3 seconds. It's 2.2, 2.3 seconds to have a VM up and accessible.
There's one caveat to that, and that is when you've just created a new image, the
Sure.
the cluster needs to be primed, it needs to be pulled in, and because macOS images tend to be really large, I think we're looking at 90 or 100 gigabytes, that the first launch can take a few minutes, I think 2 or 3 minutes. The network is really fast, but it still takes time to download that image. I believe there's work in progress to pre-warm a cluster with images. So once you've created a new image, that it'll be shipped out to the nodes ahead of time, so it's there on demand. But if you know that, you could potentially also maybe do something manual to get it on nodes, if that's really a concern. For us, it really isn't, because our system is designed to retry. The worst thing could happen is a job gets started, it takes 3 minutes to launch the image, then a job takes 8 minutes and runs over the threshold. It'll be retried in a couple of hours, so we wouldn't lose any sleep over that.
The nice thing there as well is that the Orka API, if that image is cold and it needs bringing onto the physical host machine, which only happens when you've done an update to the image. But if you are in that situation, the API doesn't time out until well after the amount of time that it would take to take that image. So you can still just fire and forget the API request and just say, please launch me this image. And yes, it might not take 2 seconds occasionally, it might take 3 minutes occasionally, but it's still, everything still just works. Everything, you just have to make that one API call to get that image. Sorry, to get that VM.
I'll just further Sven's point. Yes, so the preconditioning, which is essentially for those of you a little more knowledgeable about Kubernetes, we're allowing you to manually write to cache on the node the image, so you'll get that near instantaneous deployment. And you can automate that through the CLI, and we'll eventually have that in the API as well.
We look forward to that.
Sven, as you mentioned, you did answer a few more questions. Do you mind going over those so that the rest of the audience can hear those questions and have a bit of a dialogue about them?
Yes, of course. So the first one is, can you tell us a little more about how many images you manage and how frequently you update them? So we do run one image per Swift and Xcode version, which is 4. We always cover the latest 4 Swift versions, and we only really update them when the new version comes out. And that can be like sometimes it's a patch version, like Swift 8 starts at Swift 5.8 starts at 5.80, and there might be a 5.81, and that we typically also then update for that version, and that might make a new image. But that's the frequency is really determined by Swift version releases and nothing else at this point. And the other question is, any caching you do to avoid repetitive operations, for example, to turn the big Git clone you do into a smaller Git pull? We do shallow clones, so we only clone. You can do Git clone and then fetch depth, so you only get the latest revision. It's effectively as if you'd zipped up the repository. You don't get all the history that way, and that's what we do to keep it slim. We don't have a caching layer beyond that because we haven't really needed it. We haven't seen the need for it. And I guess it would be kind of complex to inject that because we operate the same way you would operate when you check out a package. If we were to cache it, we'd have to inject that somehow. We'd have to step in between you running git clone, and we'd have to reconfigure where we look to get git URLs and that stuff. It has been fine this way, and it's just way less complex to set up.
Fantastic.
There's another question.
Oh,
Do you
wonderful.
use GitHub's registry to store your OCI images? No, we're not. We're currently just, I assume, Andrew, there's an OCI registry under the hood, which we're sort of effectively using, but we aren't currently explicitly pushing images anywhere. We discussed this just recently for another use case of ours, where we also want to have locally have access to the images for testing. Sometimes a build might fail, and one of the great advantages of running this virtualized is that we can actually run builds on the same image that the build system is running. Like previously, that was not possible, really. We'd have to SSH into the Mac Minis, into the bare metal Minis, to try and run a build, which can be really awkward. And having the ability to run the same images locally is a huge advantage. But we haven't actually pushed any images yet for us to use them locally. But it's one of the things we'll do next. My understanding is there's nothing really required other than having access to an image registry, and then just pushing the images, because under the hood, that's a very common concept that's how Kubernetes effectively gets access to its images.
Thank you. All right. So are there any final thoughts or questions that we might have before we wrap up our session? Okay. Well, again, thank you everyone for joining us. Thank you to Sven and Dave and Andrew for all your help. We will be sending this session out, as we stated before. This has been recorded, and we look forward to any additional feedback that you may have. There will be an email address that you can contact in our follow-up email. Have a wonderful day, all.
Thanks, everybody.
Everybody.
Thank you. Bye-bye.
Bye-bye.